So now that we understand the definition of an exact differential equation from the previous video, this slide just summarizes the mathematical theory behind it. If we have a function f that changes because we change two variables x and y, we can express the total change by considering the partial change in each of those two variables. These slopes can be differentiated once more, but this time with respect to the other variable, and the equation is exact if we can prove that that second derivative results in exactly the same equation, regardless of the order in which we perform the differentiation. So now we're going to use this principle to derive the Maxwell slope relationships by applying this theory to our four fundamental equations. So if we now consider as an example this fundamental equation, dH is equal to TdS plus VdP, what we need to realize is that in this case, enthalpy is expressed as a function of the changing variables entropy and pressure. So this means that if I want to draw some parallels between my mathematical expression, this group of terms should be equal. This is the slope, first slope, and the change. Second slope, or the partial change, multiplied by the extent. What we can further recognize is that the temperature, therefore, is the placeholder for this partial derivative, which represents the slope of our enthalpy change with entropy when the pressure is kept constant, and that the volume here is the placeholder for this slope, which relates how the enthalpy change with pressure as the entropy is kept constant. And also, temperature, which is this slope, is therefore equal to m, and the volume, which is this slope, is therefore equal to equation n. So now that we know where each of our thermodynamic variables fits into the mathematical scheme of thing, which is a slope, which is a variable, we can apply the second derivative to our slopes to derive a Maxwell slope relationship. And this is our first Maxwell slope relationship that we have derived, which says we can now, because we know our equation is exact, relate the slopes of different variables on different graph systems. We can now, by applying the same principle to all four of our fundamental equations, derive the four Maxwell slope relationships. So, as one last example, if we consider this first fundamental equation, we realize that this temperature again is the placeholder of that slope, minus pressure is the placeholder of the second partial slope, U is F, S in this equation represents X, and volume is equal to Y. So the Maxwell relationship can be derived by taking the slope temperature and now differentiating it to the volume while keeping the entropy constant. And this must be equal to taking the partial derivative of pressure to entropy while keeping the volume constant. So make sure that you can apply this principle to each of the fundamental equations. See if you can, on your own, see which of the variables relates to f, x, y, and the two slopes, and subsequently derive the Maxwell relationships. It is important to remember that if we have a partial derivative, it must have its friend, the subscript, to tell us I'm changing something while I'm keeping something else constant. The purpose of this slide is to help you out in recognizing, for instance, in this fundamental equation, that here the Gibbs free energy is expressed as a function of temperature and pressure. If we want to consider the total change, we have to evaluate the partial change in variable 1 plus the partial change with change in variable 2. And how does that relate to the slope equations and subsequently get you onto defining the Maxwell relationships.